be great.
So I'll record. I don't know, last time my recording did not work, but now it seems to work. Whatever was the trick. So you want to go Homburg, maybe this one, Homburg luminosity files, those ones?
Um, yes.
Okay. Can you see this?
I actually can't.
Oh, okay. Maybe I forgot. I forgot to share. Okay, here it is. Can you see now?
Yes.
Okay, good. So maybe the first file?
Yep.
Okay. Okay. So what is confusing about this?
Well, I just haven't seen it before.
Okay, if you want some help, okay, so let's just, if I go over here in the weekly activity, so now we're in the week 6, and if you go to the lectures, okay, so it's first one, okay, so the lectures about thermal radiation, black body, and luminosity. So if you click here, here is the luminosity video. So that's what, did you watch this video?
I didn't watch any of the lectures. No.
Why?
I don't know. I was gonna get to it today, tonight, or tomorrow, and the next day.
Okay, fine. So you were hoping that somebody else will be here as well, and then you can just like join and ask the questions. So here is that video lecture. That's actually really like, you know, not that hard, honestly, except for that last file where you have to do some numerical calculations. Everything else is more or less the common sense. I had some students today in my office and we went through this and it was like, you know, really simple. But since you're here, like I could help you a little bit if you want. So luminosity is simply the energy that the star gives you from its whole surface. And so in this lecture that I recorded, I explained that that's very similar, like, you know, when you're like, you know, cooking something and you're like in front of your stove, you know, like if you have like a big pot of water and you want to like heat it up quickly, you know, you have 4 selections over there as you're looking at your stove. Which one are you going to choose?
The bigger one.
You're going to, exactly, if the pot is big, you take the big one. Why do you take the big one?
It's more surface area.
From which the heat will be transferred, right, to basically your pot. And then also you can then, you know, turn the knob. You can choose like if you want like low temperature or high temperature. If you want to do it quickly, what are you going to take?
The highest temperature.
Because obviously then the energy, you know, that it's produced by that stove element depends on the temperature. So it's exactly the same with the stars, okay? Exactly the same kind of a common sense that luminosity is going to be proportional to the size. And then now when we are talking about the stars or the spheres, what is that size proportional to? Do you know?
No.
Well, yes, you do. So I don't care about pies and fours and things like that. But if you have like a circle or a sphere, yes, what will be the area of that object be proportional to? How do we describe circle? With basically radius, yes, you agree?
Yes.
Okay, so how do you find the area of a circle? What is it proportional to? Just the radius or like radius squared or radius cubed?
Radius squared.
Very good. So the same with the sphere, right? So it's either the size of the star, or this is supposed to be R, or like, you know, radius square. Radius square gives you the size of the star. And then it depends on the temperature, but it really depends on the temperature. It's very sensitive to temperature. So basically temperature to the 4th power. And so this is your formula that you're working with, okay? And it's very common sense. And for most of these exercises, you don't have to do any calculations, okay? You just like reason basically using this kind of a concept. So then what do you say over here? You have, if you're now like, I'll give you some time, read this and then see how you're going to do this, because this is very simple.
Okay.
Mm-hmm.
So it'd be A is the largest, and then
Yes. Mm-hmm.
it looks like B, C, and E are all the same size,
Very good.
and then D is the smallest.
Exactly. Okay. And then the next one is asking you to rank their temperatures.
It looks like A and E
Mm-hmm.
are the lightest, and then
So hottest based on whatever, they're using color coding, okay, and then
and then C, and
mm-hmm.
then B and D.
Yes, very good. Okay, see, I told you it's easy. And
Yeah.
then about the C, what do you say about the C? So the C is now ranked the total energy output or luminosity from greatest to least. I'm going to go back to the picture. Which ones give you the most energy?
A, E,
Because why A?
they're the hottest.
And not just that it's hottest, but it's also
The output of the energy.
no, but the output of the energy depends on two things, the size and the temperature. So not
Um,
just that A is hottest, but it's also,
the biggest.
yes, very good. So you have no doubts, right, that it's going to give the most energy. And then,
And then E,
mm-hmm,
and then C,
mm-hmm,
and B, and then D.
yes. See? Piece of cake. Okay, so then let's see the next one. I did close the homework. Okay, so I'll have to go back to the homework. Okay, so it was the number 6. Okay, and then homework, and then luminosity. So number 2, for example. Okay, number 2. Okay, this is exactly the same thing now, except that we now have like a graph. Okay, so it's not anymore the picture, but now you have this graph over here. So what do you say? Take some time to read if you want, and I'll erase this and wait for you.
Okay. Okay.
Mm-hmm.
So it'd be A, B, C, D.
Yes, very good. Okay. And then it tells you rank the luminosities of the stars, the same stars and their luminosity.
It looks like they're all on the same level of luminosity.
Uh-huh. So they all have the same luminosity, okay? But they have different temperatures, okay? And so then the last question is basically asking how is that possible? So rank the surface area of the stars from largest to small. So I'll go back to this. So they have different temperatures, but they have the same luminosities. Okay, so this is the same, luminosity is the same, but temperatures are different. So they have to have different sizes, right? They're not the same size. Which star would be the biggest?
I'm not really sure on this one.
Why not?
I just don't get it. I understand what you're saying. I don't know the answer. But
Okay, fine. But so when you're looking over here, let's compare A and D. Okay, A is like really, really hot star. Okay, and then let's say D is pretty cool. D is like kind of as cool as it gets. The stars are not like much cooler than 3000 kelvins. So how can a star that have like low temperature give
it'd be
as much energy as the one that it's like, super hot?
it'd be way bigger.
Exactly, exactly. So that's the whole logic over here. Very good. Okay, so then that's it, basically. Now you understand it. So the largest one will be which one?
D,
Uh-huh, and then?
C, B, A.
Yes, very good. And if you just like, if you want to stay maybe for a second here, so let's say if this is like, 3000 kelvins, and this is, let's say, almost like, maybe it's like 18,000, I don't know, looking at this graph. So star A is like 6 times as hot as star D. That star actually, just like, for that temperature would give you so much more energy, because you would need like, so one would give you energy proportional to T to the power of 4, but the other one you would need to do 6 times the temperature to the 4th power, and that means like 6 times 6 times 6 times 6 more energy just because of that temperature, right? So that actually tells you that if this like, cooler star gives you the same energy as this like hot star, this one has to be like really, really big. It has to be like really big.
Yeah.
Okay, very good. Okay, let's do then the next one. And this is like all good. It's a good introduction to like, where we are going to, and that's the evolution of the stars, because that like, those luminosities will be important when we study the stars. Okay, what do you say here? The similar type of graph.
So they're all the same temperature.
Mm-hmm.
So it'd be all stars are the same temperature.
Okay, yes, all have the same temperature. How about luminosities?
A, B, C, D.
Very good. A has the greatest luminosity, as you can see. Okay, and then the third question is rank their surface areas. Which one? So first of all, how can they have different luminosities when they have exactly the same temperature?
By the size of the star.
Exactly. There is only one reason for that, and that's basically the size of the star. So which one is the smallest?
D.
Yes, and then?
C, B, A.
Yeah, that's it.
Okay.
Okay, you feel better now about this?
Yes, I do. Thank you very much.
Okay, good. Okay, here is another one. Very similar.
So it's going to be A, B, C, D.
Very good. And then luminosities?
D, C, B, A.
And then the sizes. Which one is the biggest?
D, C, B, A.
How do you know that?
Because D has the highest luminosity but lowest temperature.
Very good. Very good. That's it. So it's quite simple, So for example, just like to make it relevant, for example, the star, like something like C, that's the temperature of our sun right now, 6,000 Kelvin. And here is the luminosity. So sun would be somewhere below C. But as the sun evolves, it's going to become a red giant. Maybe you heard of it. So then it's going to be basically like this D point. It's going to be cooler overall, lower temperature, but it's going to give way more energy than it gives now. So at that point, when the sun becomes red giant, there will be no more life, like period, on the earth, right? All of the oceans, everything will kind of evaporate because the sun simply will be like, sending out too much energy. But eventually then after that, like, red giant phase, the sun will end up as a white dwarf. And the white dwarfs are going to be super hot, as you can see, maybe like a star A over here. But because they're very small, they don't give that much energy out. So our sun will kind of move through this diagram as it evolves. And so that's what these things are like preparing us for. Okay, so now let's do the last one. The last one maybe is the hardest, because it actually now involves like calculating. Okay, but the formula is still the same. Okay, so take some time if you want and read, and I'll just like wait.
All right, thank you.
No problem.
So you would just square the surface area and then...
Okay, so surface area is actually already given to you. You know this R squared that we said, that's actually the area.
Oh, okay.
So that they're even helping you with that, right? So you have the surface area, but the temperature is given as the temperature. It's not like, raised to the fourth power. So what would you do?
You would raise the temperature to the fourth power.
Okay, very good. You want me to wait if you want to do that and then tell me which one has the greatest luminosity? Because students usually make mistake. Which one gives the greatest luminosity out?
Okay, yes. I'll make the calculations now.
And I can help you actually if you want before you do. Because like, look at all of these temperatures, right? They're in thousands. And so when you think about it, like, 1,000 or 2,000 or 3,000, when you raise that to the fourth power, all of them will have this like 1,000 to the fourth power, okay? And that just simply means 10 to the 12th. So you can ignore this, like, zeros, and you just focus on the numbers over here, right? Because squaring these numbers will actually make the difference, right? We'll tell you which one gives more luminosity. So in other words, like make 3000 just like 3, and make 2000 2, and make 1000 1.
Okay, thank you.
Mm-hmm.
So 1 to the 4th is just 1.
Mm-hmm.
And then 2 to the 4th, I'm not sure, but
that just means like, 2 times 2 times 2 times 2, right? So we can do that even without the calculator.
So that's 16.
Uh-huh. And so if I were you, then I would just like, write this, okay? So for example, you can say like, 1, you said raised to the power of 4 is like 1 times 1 is just going to be 1, yes?
Yeah.
Okay, let me see why this pen doesn't work. So I would just like put here 1, basically. Here, what did you say? 2 raised to the power of 4 is?
16.
And then times 1 is just going to be?
16.
Okay, very good. And then how about C?
It's going to be 16 times 2, which
Yes.
is it 30? No, 34 or
32, yes.
32.
32. Okay, and then how about this one, D?
It's going to be 108 times 2.
So what did you get for it? So 3 times 3 is?
9.
And then so 9 times 9, basically. That's what you have over here. And that is how much?
81.
81. And then times 2?
162.
Yes, 162. Very good. And then what do you get here for E?
You're going to get 2 times 1.
Mm-hmm. Which is just 2. And then how about F?
16 times 4.
Uh-huh.
Which is going to be 64.
64, good. Okay, that's it, okay? So now once you did this calculation, it's easy to compare them.
Yeah.
Okay.
So it's going to be D,
Mm-hmm.
F, C, B, E, A.
Mm-hmm. Yeah, very good. Okay, so that's here, that's the luminosity. So then what else would you like to go over?
Let me see really quickly.
Okay.
How do I go back to my screen? Or
I don't know, maybe I can stop to share. Okay, let's see. I'm gonna stop sharing. So now
okay,
can you go to your
that works. Thank you.
Mm-hmm. So, okay, so the Doppler shift, here it is. Okay, you've done this one?
No, but I remember reading about it.
Okay, good. Yeah, a student came today to my office. She said that whatever was on Mastering Astronomy tutorial was very useful. And so what do you say then? Again, you can take your time if you want to read this, and I'll just wait.
All right, so I'm going to read it.
Mm-hmm.
So it's going to be A has the highest, C, and then B.
Well, it's asking you which one is like, getting the highest pitch or frequency, highest frequency.
Yeah.
And so that's not going to be A, because A is this person like, that sits in the train and moves with the train. So he hears whatever the train is like emitting. That's the pitch, right? But these two observers like B and C, they will hear different than what is basically emitted, because the train is moving with respect to them, right? And so now I don't know how Mastering Astronomy did it, but like, usually in like episodes that I send you, people will say, okay, the wavelengths get compressed when you're moving, towards when the source of, let's say, sound or light is moving towards an observer. And you can see that on this picture, right? This like, dashed lines, they represent the wave crests. And you can see how wave crests are much closer together here than here, right? Here they're like, more spread out. Yeah. And so that means that if the wave crests are closer together, then the frequency is higher. And so this observer C would actually receive a higher frequency than this one in the train, and definitely higher than that one.
Okay, that makes sense.
It does make sense, like, so people like explain it that way. I don't like that way particularly, but it makes more sense, like, really what happens over here, what the physics is, this emits the wave. Okay, the wave will take some time to reach you, but then like, this is at the same time moving towards you. So then like, it emits the wave again, but now there is less distance between you and the train. So the wave will take less time to get to you, right? So you're going to basically hear it like sooner, and that causes this frequency basically to rise. So as long as this is moving towards you, the distance is constantly shrinking, and that's why you hear that higher pitch. And you know that from everyday life, if you have the ambulance running by or something like that, you really hear like a higher pitch as they're approaching you, and then it kind of goes to the lower one as they move away from you.
Yeah.
Okay, good.
You can also see the line, the dotted lines. They're closer to the guy, to the B guy than they are with the B.
Yeah, I think the picture is really good. It wants to kind of like, make that point like visually. So that's perfect. I like the Center for Astronomy Education. I think all of these materials that they developed are like, pretty good, like to aid the understanding.
Yeah.
Okay, then the other ones.
It's gonna be B the longest, then A, then C.
Perfect. Okay, perfect. That's it. Okay, good. Then the next one. Okay, take your time to read.
So it's going to be E, I think, with the greatest blue shift.
Okay, and why do you say that?
Because he has the longest arrow, meaning he's going the fastest towards the observer.
Very good. And the Doppler shift only depends on the speed, right? So the faster you move, it doesn't matter, even if the E was closer, right, to the observer, but it was moving faster, then E would still give you the greatest blue shift. Good. So E is the greatest blue shift, and then?
Then D. And then B is going to be no shift.
Very good.
Then C, and then A.
Perfect. That's it. Okay. And then number 3. Okay. Now this one is like so like, there are too many of them, okay? So, I usually do like a ruler and I draw like a line to be able to answer this. But let's see. You read and tell me what you think.
Okay. All right, so the largest.
First, tell me, what do you do over here? How do you make your call? What do you need to do?
You need to look at the blue and the red, and you need to see which one is the farthest to the left, that would be the greatest blue shift.
Okay.
And the one that's the farthest to the right would be the greatest red shift.
Fine. But you can also, like, you know, just take like one line, for example, this one. Yes, this first lab spectra tells you how the lines, where they should be if this source is not moving, right? And so, for example, this line should be there. Okay. And I'm going to try to like demonstrate this with this. But then, like, you know, you draw this, okay, that line should be there in this pair and should be here, right? And then it should be like somewhere here. And then see, this is why I need ruler, and then should be like, you know, here and now here, okay? And so if that line, you can immediately see, okay, it's in the star E, it's exactly at the same location where it should be. So this star shows you no Doppler shift, yes?
Yeah.
Okay, and that can be for a reason that maybe it's not moving or it's moving sideways, right, with respect to us. But all of the other ones are shifted a little bit, okay? And so now you look at this line, and what do you notice? In the star A, it's shifted in this direction by this much, yes? You agree?
Yes.
Okay. In star B, it's shifted to this direction by this much. Here, it's shifted that much. And then here, it's barely shifted, but in that direction, and then no shift. So it's now asking you rank the size of the Doppler shift from the largest to the small. So at this point, we don't care if it's moving towards us or away from us. We only care about the size. So which one has the greatest size?
C.
Yes, and then?
And then B, and A, and D.
Perfect, that's it. And then the smallest or no is E, right, at the end?
Yeah.
Okay, very good. Then the next thing, it's asking you to rank the moving fastest towards you, and then basically moving fastest away from you. So which ones are moving towards you?
B and D are.
Uh-huh.
So then B is going to be first.
Uh-huh.
And then D.
Mm-hmm.
And then C, and then A.
Well, technically speaking, E, because it's no shift, right? And then?
Yeah, and then C, and then A.
No, and then A, and then C, right? Because you should finish with the one that it's moving fastest away from you.
Oh, okay.
Right?
Yeah.
Okay, good. So A and then C. Okay, that's it. C. Where is it? I want to erase now this before I go to the next one. Okay. So clear.
That line method really helps. It makes it easier.
It does for me as well. Like, you know, that's the only way how I can see this. Okay. And then let's see the last one. The last one, these are all interesting and different. Okay, so here is the last one. What do you say about this one?
So the largest is going to be E.
And, you know, again, I would do the same thing. I just like, you know, like writing things because I usually was like pretty sloppy and made like, you know, mistakes. So I would always go and write over here. Okay. So this one shows no shift, right? Zero shift, but 650, yes, is like minus basically 6, right? It's like 6 less than what we have over here. And then 663 would be what? Plus
7.
7, very good. And then how about this one?
+1.
+1, yes. Okay, +1. Okay, and then this one?
-10.
-10, very good. So then immediately this tells you, like, you know, how to rank the size of the Doppler shift. Which one has the greatest shift?
E.
Very good. And then?
B.
Yes.
A. D and C.
Very good. And then I think, okay, I'm going to move this a little bit. And then it tells you to rank which one moves fastest towards you. And then basically to follow the sequence to get to moving fastest away from you. So which one is moving fastest towards you?
B is.
Which one?
B.
I don't know. Is it B?
Oh, no, it's E.
It's E. Why?
Because it has a shorter wavelength.
Yes, very good. So the blue shifted ones, the ones that move towards us, they're actually blue shifted, and that means less of a wavelength. So -10 is the one that is moving fastest towards you, okay? So E and then?
And then A.
Mm-hmm.
And then C. And then D and B.
Okay, perfect. That's it. Good. And then what did you say? The writing prompt?
Yeah, if it's possible to go over that would.
Well, let's take a look at it. But I think that's fairly simple. I always say that, right? Let's see over here. But this one really this week is just like basically watch the video about the James Webb Telescope, you know, that's the new telescope that, well, it was supposed to be launched like even last year, but there are like delays, but it's going to replace Hubble Space Telescope. Very interesting. So watch that video and then basically they will tell you over there the main goals and you just like summarize that. And then also I have the videos about interferometer and then a little bit of the local history with the Palomar telescope.
All right. Yeah, it looked kind of simpler, but
it is pretty simple. This is just like kind of a reading and writing. I find these telescopes like, you know, very interesting. The James Webb Telescope is absolutely like fascinating. So hopefully like, you know, that will be impression that everybody gets. Interferometers are very interesting because they have unique way how they work. And then Palomar Observatory, like, you know, I don't know if have you been there at the Palomar Mountain and the observatory?
No.
Okay, it's very nice. Actually, it's nice for a hike. And then it's free to go up there. They have great visitor center. They talk a lot about the light pollution. And then actually, like, you know, this observatory was like for 50 years, that was the biggest optical telescope in the world. So it's kind of a really amazing, like living in South California for like a long time. This was, and still is actually, but for a long time was really like, you know, the place in the world where we push the limits of our understanding of the universe. Mount Wilson, I don't know if you've ever been there. That's just like above Pasadena. That's where the telescope is, the big telescope. And that one discovered that the universe is expanding. That's where the Edwin Hubble worked on. So there is a lot of like, you know, astrohistory over here in South California.
Oh, I didn't know that.
I know. Well, usually people don't, right? Unless you're like an astronomer. But it is like, you know, if you're from here, you know, you kind of live in a astronomy, really important part of the world.
Wow.
And you can actually go and visit all of these things. One of my, so I'm going to stop recording this. One of my former students